Okay, in this video, let's talk about section 5.2. Properties of rational functions. Okay, so what is a rational function? We know that the rational numbers means that you have two integers, 2 over 3, 4 over 5, and 11 over 3, something. So the rational number is the ratio of two integers. Rational function is the ratio of two polynomials. Okay, so a rational function is a function of the form r of x equal to p of x over q of x, where p and q are polynomial functions. And we know that the 0 cannot be the denominator. So here q is not the 0 polynomial. It's a polynomial, but it's not constantly 0. Okay, so this is the definition of a rational function, a polynomial p over a polynomial q. Here, q cannot be a constant 0 polynomial. And the domain of a rational function is a set of all real numbers except those for which the denominator q is 0. Okay, so what does this mean? This just means the domain is the set of all real numbers so that q of x is not equal to 0, except those for which the q is 0, so we just remove them. Okay, so that's the domain. For example, if we have a rational function 2x squared minus 4 over x plus 5, in order to find the domain, we need the denominator not equal to 0. X plus 5 is not equal to 0, so x is not equal to negative 5. So we can write this way: negative infinity to negative 5 union negative 5 to positive infinity. So by this way, we can just simply remove the negative 5. We use a round parenthesis. Round parenthesis does not include the endpoint, so in this part there's no negative 5. You can write this way, you can write this way, either works. Second, we have this rational function 1 over x squared minus 4. Then what is the domain? The domain is a set of all real numbers except those for which x squared minus 4 is equal to 0. Except those are numbers. So in order to make sure, in order to find the domain, we find the solution and accept them. Okay, we find the point that make it 0. So x squared minus 4 is 0. Effected is x minus 2x plus 2. So x is 2, x is negative 2. These two are the solutions of a denominator equal to 0. Okay, so you accept 2, accept negative 2. This is and. If you want to write a word, it's and. It cannot be 2 and it cannot be negative 2. Okay. And 3. The rational function is x cubed over x squared plus 1. Then the domain is set of all real numbers except those for which the denominator is equal to 0. But we know that x squared plus 1 is never 0 because we are talking about the real 0. Whenever we say 0, in this part is a real 0 because this is a set of all real numbers. This one, if you check discriminant b squared minus 4ac, b is 0 minus 4 times 1 times 1 is negative 4, less than 0. This polynomial, this quadratic function has a negative discriminant, so it has no real solutions. It has no real solutions. It's just a set of all real numbers. You don't need to accept anything. Sorry, you don't need to accept anything. For the domain r of x is equal to x squared minus 1 over x minus 1. Okay, so by the definition, the domain is x, so that x minus 1 is not equal to 0. Okay, and this just means x cannot be 1. So the domain is from negative infinity to 1, union from 1 to positive infinity. So it cannot be equal to 1. This example, let's say a few more words. We know that x squared minus 1 can be factored as x minus 1, x plus 1. If you know this factorization, x squared minus 1 over x, you see, we can cancel x minus 1. We get x plus 1. But this identity works, or this identity holds 1, x is not equal to 1. So it is an identity, correct, but it's not identity for all x. It is only the identity when x is not equal to 1. When x is equal to 1, the left side is well defined, but the right side is undefined. So they are not equal to each other. Okay? So whenever you do this cancellation, you actually cancel a non-zero number. You cannot cancel 0. we don't have that type of property. Okay, so these two things are different, even though they are almost identical, but they are different at one point. So these two things are different. This is a function which is not defined at one. This is a function defined everywhere. Okay, so be careful when you talk about the domain. You do not do any simplification. Just study the solutions of a denominator. Okay, so like this part, we have some name. This name is only used in this textbook. If R of x is equal to P of x over Q of x is a rational function, and if P and Q have no common factors, okay, then the rational function R is said to be in lowest term, in lowest terms. Okay, so if you cannot, basically they don't have a common factor, so you cannot do cancellation. So for those four examples, the first one and second one and third one, they are in lowest terms, but the fourth one, it is not in the lowest term because the numerator and the denominator have the common factor x minus 1. Okay, so that's the lowest term. When you have a lowest term function, if R of x is px over qx in the lowest term, and let's say, what is the x-intercept? The x-intercept is R of x equal to 0, is a solution of R of x equal to 0. R of x is a numerator, a rational function is 0 if and only if the numerator is equal to 0. So it's equivalent to P of x equal to 0. Okay? So the meaning, the 0 of the numerator has some geometric meaning. The 0 of the numerator has a geometric meaning. It provides x-intercept. And the q of x equal to 0. The solution has zeros not in the domain. They have, because we are going to accept those numbers. So they will also give us some geometric quantity, geometric object in the next topic. Okay, so q of x equal to 0, it has geometric meaning. P of x, numerator equal to 0, also has a geometric application. we will see what they are one by one. Okay? But check here, we have a condition when we have a rational function in lowest terms. If they're not in the lowest term, it's not that way. Example. Graphing. Y equal to 1 over x, y equal to 1 over x squared. Y equal to x, the reciprocal function, we actually graphed it before in the section of library of functions. We did the graphing. So it's like this. It has two branches. It's an odd function. One branch is in the first quadrant. The other branch is in the third quadrant. There's no definition at 0. So there's no y-intercept, and the numerator is now 0. So it has no x-intercept, no intercept at all. Okay, so this is y equal to 1 over x. If you sketch y equal to 1 over x squared, this time, you see you have square, so the value is always non-negative, and the numerator is 1. There's no 0. If you want to get a 0 solution, numerator is 0. But here numerator is 1, you cannot have 0. And if you sketch it, it will have a similar shape, but this time it becomes an even function. The left to right even function. Okay. Just plot them. But it will change very fast. If you have a half, you will get 4. If you have a 4, you will have half. 1 over 16. So something like that. It's a very by hand. It's not easy to sketch. Okay. So this is a graph. Let me see. There is no x, y intercept. No x-intercept. Let's explain. No x-intercept is because it's called fx. Fx equal to 0 has no solution. No y-intercept, it's because 0 is not in the domain. Okay, so they have different reasons, but we just say they have no x and y-intercept together. Okay. And it's an even function. It is an even function, and when x approaches 0 from either left or right side, you will get an extreme large value. When x approaches a positive infinite or negative infinite, you will have almost a flat graph. Okay, so that's 1 over x squared. Now let's do some transformation. We have 1 over x minus 2 squared and plus 1. You can there are two transformations. One is a horizontal shift, the other one is a vertical shift. You can try either directions. In the book, they try the horizontal first, the vertical second. Let's use the other order. So first, you get 1 over x squared. And then let's shift it. 1 unit up. This is 0. 1 unit up, this is 1. Okay, this becomes 1 over x squared plus 1. And then we are going to shift it to the right. It's x minus 2. So you're going to horizontally shift it right 2 units. I draw this dotted line. When we shift it up, it's kind of a this x-axis is shifted to this horizontal line y equal to 1. You shift it to the right, it means more or less you shift this axis, y-axis to the right 2 units. So that's why I draw this dotted line. And then we get this. You can compare this with a graph in the book. This is 1, this is 2. Okay, the same thing. We already discussed something so-called asymptotes in the discussion of hyperbola. And here, let's systematically define and study it. At that moment, we can only give you the geometric idea. But here, let's see. The geometric idea is the same as a hyperbola. Hyperbola, you have across two x and two asymptotes. Here's a similar thing. You see here, I mentioned when the x is close, use this one. When x is close to some point, your graph will be very, very close to a vertical line. Or when x approaches infinity, your graph is very, very close to the certain horizontal line. If this is the case, we will call them vertical asymptote and horizontal asymptote. Okay, so that's a vertical asymptote and a horizontal asymptote. And in the hyperbola, it's not vertical, it's not horizontal, it's called the oblique asymptote. Okay, later. So let R denote a function. Not just rational functions have asymptotes, so that's why even though we still use the symbol R, but it represents whatever function. If as x approaches infinity or as x approaches negative infinity, you can approach infinity either to the right or to the left. The value of R of x approach the values. The values of R of x approach some fixed number L. L comes from the limit, L, limit. Then the line y equal to L is a horizontal asymptote. Horizontal asymptote of the graph of R. Okay, so it could be like this. Okay. This is a horizontal asymptote. When x approaches past infinity, it approaches this horizontal line. This is L. It's horizontal, so it's a y equal to L. Or it could be like this. And it can also be like this. And it can also be like this. Like this, it means here, when x approaches positive infinity, you have horizontal asymptote. When x approaches negative infinity, you have horizontal asymptote. When x approaches positive infinity, this asymptote is like up and down, the shaking case, but eventually it approaches this horizontal L. Or you can have two different choices. To the left, you have one L. To the right, you have the other L. In this case, you will have two asymptotes, horizontal asymptotes. So here it corresponds to horizontal asymptotes. Okay, there are two horizontal asymptotes. Here we just mentioned there's one. And in this example, it doesn't matter you let x approaches positive infinity or approaches negative infinity, you only have one. This is just one case. Here you have two. Okay. So also from this discussion, you will see that a function can have at most two horizontal asymptotes because you can allow x approaches positive infinity or approaches negative infinity. So you have one case, you have a second case. If those two cases give you two different numbers, you have two horizontal asymptotes. If those two cases give you the same number, you have one horizontal asymptote. Or maybe just one case has a limit, has a value, the other case does not. For example, this one. Only when x approaches positive infinity, you have a number. When x approaches negative infinity, you don't have a number. Then you still have one horizontal asymptote. Okay? And the horizontal asymptote, the whole graph can be above this line or, well, I should sketch it. It can also be always below the line, like this. It can be always above, can be always below. It can also be up and down infinitely many times. Either works. We just need the graph very, very close to the horizontal line. Okay? So that's a horizontal asymptote. Vertical asymptote. If as x approaches some number c, the values ops value of r of x approaches infinity. So here we just say it approaches either positive infinity or negative infinity. It's not necessary to always positive. So we just put ops value. Then the line x equal to c. Now it's to talk about vertical. Vertical is x equal to something. Is a vertical asymptote of the graph of R. Okay, vertical asymptote of the graph of R. For example, you can have something like this. When x approaches some point c, it approaches positive infinity, or you have this case, the two branches both approaches negative infinities, or you have this case, two branches one approaches positive infinity, the other one approaches negative infinity. In either case, x equal to c is called a vertical asymptote. They all represent a vertical asymptote. And be careful, a function can have many vertical asymptotes. Okay, so for example, 1 over x has one vertical asymptote. One over x times x minus 1. At 0, you can get infinity. At 1, you can also get infinity, because when x is close to 1, this denominator close to 0. You flip 0, you will get infinity. So it has two vertical asymptotes. And, well, by this order, let's construct. When I say a rational function can have many, it means for one rational function, of course, the number of the vertical asymptote is fixed, but we can construct a lot of rational functions so that there's no upper bound for the number of the vertical asymptote. Okay? So whenever you have, for example, you say, let's find a rational function with 10 vertical asymptote, we can construct that a rational function. Let's say, let's find a rational function with 1,000,000 vertical asymptote, we can construct that. But for one fixed rational function, it has just those amounts of vertical asymptote. Okay, so this one will have 3. You can see how I do it. If you want 1,000,000, you just get x times 1, x times x minus 1 times x minus 2 times x minus 3. If you have time, you can repeat it until times x minus 1,000,000, and use 1 over it, the product. That function will have 1,000,000 vertical asymptote. Okay, so the number of vertical asymptote is not bounded. It can have as many as you want, as big as you want. Okay, so that's the difference. Horizontal asymptote, you can have at most 2. But the vertical asymptote is totally dependent on the denominator in the lowest terms. Okay, so let's see some remarks. First, a horizontal asymptote. A horizontal asymptote describe the end behavior of the graph. What is end behavior? Remember, end behavior means when x is positively large or negatively large. Positively large approaches positive infinity. Negative large approaches negative infinity. So that's the same meaning. So when that happens, you have a fixed number, then you get a horizontal asymptote. When x is negative large, you have a fixed number. You have another. Also have a horizontal asymptote. So that is the meaning of a horizontal asymptote. And as I described in this example, the graph can intersect horizontal asymptote. It's possible. It's not impossible. But if for the rational function, if we want to construct a vertical asymptote, you will see that, for example, 1 over x, then the y equal to 0 is a vertical asymptote. When x approaches 0, you will get either positive infinity or negative infinity. Or here, when x approaches 0, they both approach positive infinity. But 0 is not in the domain. 0 is not in the domain, there's no point on the graph. There's no intersection between the vertical asymptote and the graph. For the rational function, we only say rational function. So the graph of a rational function will never intersect a vertical asymptote. In other words, the graph will not cross the vertical asymptote. So it looks like the vertical asymptote build some walls between the walls in the xy plane. So over each part, the graph will be separated by the vertical walls. Okay, like what we mentioned, there's a horizontal asymptote, there's vertical asymptote, there's a third type of asymptote. It's like the hyperbola. Hyperbola has a oblique asymptote. Okay, so if as x approaches infinity, or as x approaches negative infinity, the value of a rational function well, it's not all just the definition for the rational function. It is also the definition for other functions. But here in this section, we only discuss a rational function, so we put a rational function. But it can be any other function. For example, the hyperbola. Hyperbola also, the graph has oblique asymptote. The value of a rational function r of x approaches a linear expression ax plus b. A is not equal to 0. Then the line y equal to ax plus b is an oblique asymptote. It's an oblique asymptote. Let's sketch it. This is possible, right? It is possible. It's an oblique asymptote. And so if you have something like this, we just say the graph of a function may intersect an oblique asymptote. graph of function may intersect an oblique asymptote. Okay. So let's try to locate a vertical asymptote of a rational function. To find a vertical asymptote of a rational function, basically we need an extremely large value. In order to get a large value, you need the denominator as small as possible. Okay, so that's the rough idea of the theorem, locating vertical asymptote. A rational function R of x equal to P of x over Q of x in lowest form. So all these discussions have such assumption. It has to be in the lowest form. Okay, a rational function will have a vertical asymptote x equal to r if r is a real zero of the denominator. Q. Okay, so this is the geometric meaning of the zeros of denominator. We know that the zeros of the numerator give us the x-intercept. The zeros of the denominator will give us the vertical asymptote. And be careful, vertical asymptote is not r. The vertical asymptote is not r. Vertical asymptote is x equal to r. It's a line. It's a vertical line. Okay, so this, if you want to write, okay, what is the vertical asymptote? It's not r. It's x equal to r. Be careful. Okay. Once we have such theorem, then the identification of vertical asymptote will be simple. First, if we have a rational function x plus 3 over x minus 1, then what is the vertical asymptote? So x equal to 1. The zeros of denominator is a vertical asymptote. Okay, and b, r of x is equal to x over x squared minus 4. X squared minus 4 has two solutions, 2 and a negative 2. So x equal to 2, x equal to negative 2 are vertical asymptotes. Okay. C, fx equal to x squared over x squared plus 1. This denominator, x squared plus 1, is a quadratic polynomial, and its discriminant is less than 0. It has no real solutions, so it has no vertical asymptote. It has no vertical asymptote. And D, x squared minus 9, x squared plus 4x minus 7. In order to find the vertical asymptote, let's check the factorization. The numerator is factored as x minus 3x plus 3. Denominator, you do that across, sorry, not 7, 21. 21 can be factored as 7, negative 3. Then this 1 times 7, 1 times negative 3 will give you 4. Okay, so it's x plus 7, x minus 3. Minus 3, negative 3. And you see here, this function is not in lowest term. It's not in the lowest term. In order to apply the theorem, you have to ignore x minus 3 term because they are not supposed to be in the lowest term. So you only consider x plus 3 over x plus 7. Okay? Can you read it? So, okay. So you will skip those two terms, only consider x plus 3 over x plus 7. And in that simple lowest term, x equal to negative 7 is the unique vertical asymptote. Okay, so that's the purpose of this example. We want to emphasize the theorem. The theorem works only for rational functions in lowest term. Okay, and also the formula of vertical asymptote is x equal to r, x equal to 1, x equal to 2, x equal to negative 2, x equal to negative 7. It's not just 1, 2, negative 2, negative 7. It's not that way. Okay. Okay. So that's the example. Okay. There's many other topics. Okay. Let's stop this video. We will continue the discussion about rational properties of rational functions in the next video. Okay. We finished this video. Thank you. Do exercise.